This lesson is the first of several on biological macromolecules, and here we'll start looking at carbohydrates by looking at mono and disaccharides, and in a future lesson we'll look at polysaccharides. Here are your objectives. Now, carbohydrates are molecules that have carbon, hydrogen, and oxygen, such that in general they follow this kind of formula, where n is an integer. So what I mean by that is if n was 5, you would get C5H10O5. And if n was 6, you would get C6H12O6. So they're called carbohydrates because you've got carbon and then waters. This one, for example, C6H12O6, that's the formula for glucose, as well as other isomers or rearrangements of glucose. So first, we're going to look at monosaccharides, or also called simple sugars. And you'll recall that we talked in an earlier lesson about polymers being larger molecules made up of repeating subunits called monomers. When we're talking about sugars, monosaccharides are the monomers. So we can take multiple monosaccharides and join them together, and then we will get more complex sugars. So first, let's look at glucose. Now, glucose can exist in a straight chain form or in a ring form, but an aqueous solution is typically in a ring form, and we're going to draw that like this. We're going to draw a hexagon with oxygen at the top right, and then we're going to close out our hexagon. Now, this is the first step in drawing what's called a Haworth projection, and in a Haworth projection, each of the corners is a carbon. We're not going to draw the hydrogens at all. They're going to just fill in all the extra spaces. Now, this is actually only 5 carbons, and I've told you that glucose has 6 carbons. The other one is on a chain up here. Now, we could draw this by just putting a bend in the chain, and that would indicate a carbon at that bend, but I typically break from the pattern that I had described here before, and I actually draw out this carbon just to remind myself of what's going on. So here I have CH2OH. Now, at each of these corners I've got a carbon, so that's now I've got carbon 1 here, 2, 3, 4, 5, and then this is my 6th carbon. And that's the way that they're numbered, starting from the right here and then going clockwise. Now we need to fill in the rest of this. The first thing to know about these kinds of projections is that they are tilted away from you. So this end is farther away and this end is closer. And to show that kind of 3D aspect, we draw a bit of a wedge here underneath that we fill in, and that's supposed to give you the impression of 3 dimensions, that the plane of this ring is tipped so that carbons 2 and 3 are pointing towards you. Now we fill in the rest of the atoms. We have a hydroxyl group pointing down from the ring here, and then down from the ring here, and then it's pointing up from the ring over here, and down from the ring over here. So I have this going from carbon 1 down, down, up, down pattern on carbons 1 through 4. And then carbon 5 is here, and carbon 6 is there. This pattern of down, down, up, down gives me alpha glucose. If I were to tip the hydroxyl group here upwards, like this, then that would be now beta glucose. But with it tipped downwards like that, it's alpha glucose. That's the difference between alpha and beta glucose. Now, glucose is a very important sugar for fuel. It's our blood sugar, glucose, and we'll encounter it as a monomer making up other polymers in future lessons. Ribose is another important sugar to know. So glucose, both alpha and beta, are 6-carbon sugars. Ribose is a 5-carbon sugar, and we'll draw it like this. Now we're going to draw a pentagon with oxygen at the top, like that. And again, we're going to draw our wedge structure of the Haworth projection, and that's tipped towards us. Now, here we only have 4 carbons right now. The 5th carbon, again, is sticking up over here, like that. And we have a hydroxyl group sticking up, and hydroxyl groups down, like this. I often remember the structure of ribose by thinking, yay, ribose, because to me, it looks like a person who has legs down here and is raising their hands up like this, like they're celebrating. And maybe they're at a baseball game and they've got one of those giant foam fingers on their right hand, and that's why this is larger. So if you remember that, that's the kind of silly trick that I use to remember the structure of ribose. Again, we can number the carbons. This is carbon 1, 2, 3, 4, and 5. And that's actually going to become important when we encounter ribose in the structure of DNA and RNA. RNA stands for ribonucleic acid, and DNA stands for deoxyribonucleic acid, and they're named that because they contain ribose as their sugars. And we're going to encounter these numbers again, especially the 5 and the 3, when we talk about the polymerization of DNA and RNA in a future lesson. Now, with those numberings of the carbons, we can talk about how we would link these together. Now, a glycosidic linkage is a covalent bond between, two monosaccharides, or two simple sugars. So, let's say we had one alpha glucose, like this, and I'm not going to draw the whole thing right now. Actually, why not? Let's draw the whole thing. I've got one alpha glucose here, and I'm not going to draw the carbon number 1. Remember, this is carbon number 1. I'm not going to draw the hydroxyl group coming off of it, because it's actually going to be involved in a bond with the hydroxyl from carbon number 4 of the next glucose over. So if you take a look at what I'm drawing here, what I'm showing is a glycosidic linkage between the carbon 1 of one atom, the carbon 1 of one glucose molecule, and the carbon 4 of the next. So this is carbon 1 over here, and this is carbon 4 of the next. And if you think it through, what's happened here is a dehydration reaction, a condensation reaction, where the hydroxyl group of one and the hydroxyl group of the other have released water, and only an oxygen is left behind. So in making this, we lost water. And this is called, therefore, a 1,4 glycosidic linkage. And because these are both alpha carbons that I've drawn, down, down, up, down, and this would have been down, down, up, down, this is called an alpha 1,4 glycosidic linkage. And if they were beta carbons, it would be a beta 1,4 glycosidic linkage. Sometimes you'll see joining between the carbon 1 and carbon 6, and that would be a 1,6 glycosidic linkage. So that's what we're talking about when we talk about those numbers. Let's talk about the disaccharides, molecules made up of two monosaccharides that can be formed by various combinations. So glucose and glucose gives you maltose, and that's often formed in the breakdown of starch. Glucose and fructose, I haven't shown you the structure of fructose, but it's another simple sugar, another monosaccharide. That gives you sucrose. Sucrose is what we know of as table sugar. And glucose and yet one more simple sugar, galactose, gives you lactose, and that's the sugar that's in milk. So that's an introduction now to monosaccharides and disaccharides, as well as how we draw monosaccharides and the linkages that they can form.